Thank you guys for coming out. It's been a while since I've spoken at Pi Ohio or any conference for that matter. A lot has changed. I was really blessed. I gave a talk 2 years ago at Pi Ohio, I think 2012, or that would be 3 years ago, maybe it was 2013, called Super Advanced Python. That ended up being a pretty big hit because I covered a lot of really intermediate to advanced concepts. And my hope with this talk is to refine it a little bit, focus on, I want to focus on just the functional aspects of Python, and I would, I'm trying to respond sort of to the comments that I've read on YouTube. A lot of people have given really great feedback and criticism. So yeah, let's begin. First thing I want to talk about is categories and category theory, which I didn't really get to in my talk in the Super Advanced Python a couple of years ago. I think category theory is a great mathematical concept that every developer should understand and learn to help them understand how to do data transformation. So any kind of, you know, who here, just by show of hands, is familiar with set theory, right? So you have sets, you can convert sets into other sets, you can unionize them, you can split them up, right? And it's basically the study of different groupings of collections of objects, right? Or anything. Categories take set theory to kind of the next level. Categories are, category theory is the study of objects, their transformations, and their morphisms, and their structure. So I want to go over a few, I don't know, concepts, definitions, or whatever in category theory, because I'm going to refer back to these occasionally throughout the talk. So a category in category theory is nothing other than a bag of objects. And actually, bag is a mathematical term for a collection. So it's kind of it's kind of fun. So if we think here of every single one of these dots is a object, the collection of those objects together make up a category. Morphisms are the mappings of one object to another. They are one-way direct mappings. So here we have the top center object, which is being mapped, is mapping to the object on the bottom left, and is mapping to the object on the right, and the object on the left is mapping to the center object. So morphism is just a mapping from one object to another. You have a term called a composition. A composition is two objects and their mapping together, right? So this is one item in a dictionary in Python, right? That is a composition according to category theory. This is also a composition. Composition can be made up of any number of objects that have an associative mapping between them. So here we have a composition on the left called F and a composition on the right called G, and them together make up the composition F composed of G, which you see here as, or G composed of F. This is an associative law, and it's something that, as programmers, we think of intuitively, right? Like, if I map, you know, Raymond likes Thai food, and Thai food is awesome, then it follows that Raymond likes awesome food, right? Because Thai food is awesome. Okay, that's not completely logically sound, and it's a bad example. But you know, the point is there. When we're doing any type of data translation, we're going, you know, I have this data maps to this thing, so I can map this data to this thing, because this thing maps to this thing. All category theory says, with its morphisms and compositions and everything, is that those mappings are associative. So here's another composition. This is another example. We have F, which is the top composition, and we have H, which is the composition, or the mapping going down into the left, or down into the right. And those together, right, make up a composition. And we can infer a new morphism between the node on the top left, the object on the top left, and the node on the bottom, and call that H composed of F. You also have a concept of identity. Identity is pretty simple. A maps to A, B maps to B, Not super important for this talk, but interesting. So again here, if A maps to B and B maps to C, then it follows that A maps to C. Right? We call this an associative composition. And for, how's this doing? Should I move it up? Or is it okay here? Is that all right? All right. So identity, A maps to A, B maps to B, as I said before. So the associative law in category theory says that if I have a composition F of G, F composed of G, and that can compose with H, then F can compose with G, which is composed with H, right? Let me show that here in a little bit further view. So I have a series of objects here and their mappings. The base mappings are or base morphisms, arrows, they're also called, is H, G, and F, right? So the center object only has this mapping G to the bottom object, and the bottom object only has this mapping F. But if I compose them together, I get F of G. If I compose F of G with H, then I end up with F of G composed with H. If I end up with F over here and G of H over there, then I end up with the same composition, F of G of H. They are the same, even though they're I don't know, split up differently, because associations map directly. All right, so quick recap. In my 2012, 2013 talk, I talked about how everything in Python is an object. And what I was trying to drive at is that when you understand functional programming and you understand that functions are a first-class object in Python, there's like this deeper beauty, right? You learn to realize that I can do anything I want with functions in Python, like anything. I can turn any object into any other object. I can translate any data into any other data at will. And that is like hugely cool in my opinion. So if everything in Python is an object, this is sort of the proof. Categories and groupings of objects, and if categories are groupings of objects and their mappings, then everything in Python can be grouped into categories. And then we can transform categories into other categories by applying functions to them, which I'm kind of going to get to. So categories can be transformed into other categories via functions. So if I have a group of mappings, a dictionary, right? A dictionary is just a group of mappings. A dictionary is the basic idea of a category. I can map that to anything else that I want it to be. And that dictionary can be made up of other objects or other dictionaries or other lists. And I can translate that to other stuff. And that seems pretty obvious and cool. But and this is really cool, that I can translate and do whatever I want. But what's even cooler is when we think about set theory doesn't really care about order or structure, because sets are unordered collections of distinct items, right? So set theory tells us that we can transform any set into any other set with functions. But category theory tells us that we can transform any category into any other category with functors, which apply mappings over that entire category. Here's the kicker. Set theory doesn't preserve order or structure. Category theory does. So we can do some really awesome, amazing things with it. And that's sort of the underlying theory behind why Python is such a powerful language at its core. So let's talk about functional programming in Python. We're going to start out pretty simple. We have a basic loop here. We have a list of numbers, and we are just going to multiply each item in that list by 2, and we're going to print it out. I'm going to give you guys a second to absorb this. Is there any questions about this slide? I'm going to ask questions as we go through. Pretty straightforward, pretty common code you're going to see, right? This is a list comprehension. List comprehension lets us take all of this code and compress it down into a one-liner. So on the left there, we have our functor, or our function in this case, because we have a list, although it doesn't technically qualify as a set, because in this case it does, because they're all unique items, but they may not be unique, right? So we have a function on the left, and we're applying that function to each item in this list, to each object in this list, right? Because these are numbers, and you can think of numbers as distinct numbers, but you can also think of them as distinct objects. So here we've just multiplied each item in the list by 2. Here's another one. This is a kind of an extension to the example before, where we are only going to append to the list if that particular item in the list is evenly divisible by 2, which is what x mod 2 equals 0 does. So we end up with this really big block of code, which can be distilled down to in this, where we can apply a conditional at the end of our list comprehension in order to tell us whether or not we want it to even consider that item for the list. And I apologize here on the left, that should be x times 2 for x in my list. Let's talk about loops again. This is a dictionary. So Python, and I apologize, I'm cutting off on the side here. Python has dictionary comprehensions. I can iterate through each item in the dictionary comprehension here, and I am multiplying the value of each item in this dictionary by 2. It's very similar to our example before, but I'm looking at mappings. Here is the dictionary comprehension in action, where I am. Here is the functor that I'm applying, and we're going through each list. Just like the list comprehension, we can apply a conditional at the end of this, so that you can distill down your code even further. I want to talk about functions. Pretty straightforward, right? We've declared a function, the function prints out something, we call the function, and we see its result. Let's talk about lambdas. Lambdas in Python are not all that special. It's just an anonymous function. Now you can apply a name to it. Here I have created a lambda that has a print statement on it, and I've named it, this is my function, by assigning it to, this is my function name on that first line there. And then I can call it like any other function. Here's another function at the bottom where I apply, and I apologize here at the bottom again, that should be another function inside the print statement. But I can just call the function within my list comprehension. Here is a kind of incremental step. You might go, oh, why don't I just do this in def? Well, because a lot of times you don't need the name. You could just put this in there and not have to worry about it. Let's talk about the filter built in. So there are 3, I call them like the 3 kings of functional programming: filter, map, and reduce. With these 3 things, you can do a wide majority of the kinds of things that you might want to do with data transformation. So filter here, basically, at the top here, we have that list comprehension from before, where we are pointing out, and again, this should be x times 2 for x in my list. If x mod 2 equals 0, I want you to go ahead and select those things out and then multiply them. Here at the bottom, and I apologize again for the error, should be printing 1, or I'm sorry, yeah, no, that's correct, 2, 4, and 6. These are both correct, actually. I'm freaking out. Okay, so these are both correct. So the first one here is that list comprehension from before. Pretty simple, but here we're using a lambda, and we're using the filter. What filter does is it says, for each item in the list, in this iterable that I pass to filter, I want you to apply this lambda, which is an equality check, or that lambda is expected to return either true or false. Python expects that lambda to return true or false. In this case, x mod 2 is equal to 0. implicitly returns true. Now, unlike functions, regular functions in Python, lambdas have an implicit return in them. So even though you don't see return here, it's returning that value. It passes that each time filter calls that lambda, lambda returns whether or not it's true or false, whether it matches that, and if so, it selects those things out of the list and gives you the result. The map function does the same thing, but rather than applying rather than expecting true or false, Python expects you just to return a value, and then it will take that original object and translate it into this new object, right? So we're applying a function to an item, and that function transforms that item in some way, that object in some way, and gives us a result. So here we have the same sort of thing above, where we have x times 2 for each thing. So we go 2, 4, 6, 8, 10, 12, right? Well, we can apply lambda here with map, and they're functionally equivalent. Now, I will say map is really great for, let's pretend, so why would you use this, right? Why not just use list comprehensions? And when should you use list comprehensions, and when should you use map, right? So it turns out list comprehensions are actually a lot faster in Python because of how they're implemented under the hood. So if you're going for performance, and especially if you're using generators, list comprehensions are pretty good. But say you have really complicated business logic, right? And I want to, I have a function that does really complicated things. I could pass anything to map. It doesn't have to be a lambda. I can pass any function in here and say, call this function when you encounter this object. And that function might be 100 lines of code. Do all these things to this thing and transform it in some way. I hope you've broken it up, but my point is you can do more complicated things with map than you would with the list comprehension. Yes?
The list comprehension can execute any arbitrary function as well.
That's true. Yeah, I'm not sure how to respond to that. I apologize. I think sometimes it comes down to preference, and if somebody else knows better, please speak up. The other reason you might want to do this is because you can stack them together. That's not really helpful, and I apologize. So let's just go with that. This is available to you. You can use it if you want to, and this is what it does. And I wish I knew more, and the next time I give this talk, I promise you I will. Here's the reduce built in. So reduce, you actually have to import in Python 3. It's not available by default, and I think they changed it. Was it 3 or 3.2 or 3.3? Somewhere around there. They removed it from being a built-in where it's just always available to being something you have to import, which I believe is part now of the iter-tools or the collections library. So reduce, what reduce does is it takes 2 parameters, the first, and iterates over each item in a iterable. The iterable might be a dictionary, it might be a list, it could be a set, it could be anything that implements the iterable dunder methods, right? So, so in this case, what we're going to do at the top is we have a value, and we're just incrementing that value based on whatever value is in the list, right? We could do the same thing here at the bottom, but we're first going to take the first value, and then the second value. We're going to apply the function to those. So this will return 3. So I'll get 3 here, right? And then I will take that, pass it as x, and then pass the next item. That will give me 6. So, think of like a tree here. Right now I have 6. Then I'm going to take 6 and add it to 4. So 6 plus 4, it gives me 10. And so on and so forth until I get through the end. Again, any function can be applied here. That will get you, in this case, if you multiply them together, you'll get 720. Any and all are a couple other built-ins that are useful. Any will return true if anything in the iterable that you pass it returns true. All will return true only if everything in that iterable that you pass it returns true. So, give you a second to take that in. Pretty straightforward. This is the sum built in. This is the reason they removed reduce, is because most of the time when people were misusing reduce, they were using it as a, in its basic set. And here, they say just use sum. 90% of the time when you use reduce, you're going to use sum. And that's what most people used it for a long time. There's still reasons that you might want to use reduce. It's up to you to figure out when that reason is. I rarely use it personally, but it is available to you. Sum will add all those things for you. It's equivalent to an add reduce there. Enumerate is a cool method. Enumerate will take your list and it will apply indexes to them. So anytime how many times have you had a for loop where you're iterating through items and you're like, you actually needed an index? Pretty rare, but it happens, right? Sometimes you're like, man, I actually need an index here. Like, the built-in iterable methods through a for loop in Python are kind of, ooh, there must be something out there that will actually give me an iterable, the index for where I'm at in my iterator. Enumerate does that for you. So the first item, it will say this is item 0. The second item, this is item 1. The third item, this is item 2, which is what we see here. We have zip. Zip, I'm going to switch to since I'm getting cut off here. Can anybody see this? All right, so we're going to switch to the actual code to the presentation so that I don't keep getting cut off. All right, so zip takes two iterables and combines them together. So you think of it like a zipper, right? That's why it's called zip. So I take this thing and this thing, combine, this thing and this thing, combine. And it's just kind of walking through each thing, right? So I think of like a zipper. So here I have a list of people, I have a list of foods. I've gotten this data from 2 different sources, but I know they're ordered correctly. So I know that they're mapped, but they're in 2 distinct collections. How do I combine them together? I can do that by zipping them together. In this case, Raymond likes Thai food, Guy likes Indian food, Sarah likes Mexican. So zip them together. If you didn't know this, this is another reason to absolutely love Python, is that everything kind of plays nicely with everything else. If you have a list of 2 tuples and you pass it to dictionary, dictionary will build a dictionary for you. So now I've taken 2 distinct items, I've zipped them together, and I've converted it to dictionary. Now I have one-to-one direct mappings. Chain. Chain chains 2 lists together. Chain is special because it does it with generators, not with iterators. So every time you make a call to chain, it gets that next item between the 2 lists until it hits the end of the first list, and then it goes, oh, that one's empty. I've gotten all those from there. I'm going to go over to this list. Does everybody understand the difference between iterators and generators in Python? Raise your hands if you do. Okay. So the biggest difference and why you might use generators over iterators and why this is important, let's say I have, a gigabyte of data. That's just one stream of numbers with stock market values, right? And I need to go through every single one of them. If you load them all up in memory, a gigabyte of memory, okay, maybe that's doable. I have a petabyte of data. How do I iterate through each thing? I don't have a petabyte of memory. There's no way I can hold this in my computer all at once, right? You can generate over them. You say, give me the next thing. Okay, I have the next thing. I'll work on this next thing. Give me the next thing, right? So it's rather than trying to get everything at once and looping through it while it sits in memory, you're loading things in memory dynamically while you're going through them. So that's why generators are important. Well, chain will let you chain different things together. Say I have a gigabyte of data here in one list and a gigabyte of data here in another list, and I just want to iterate through them very simply and easily, but I don't want to load them all up in memory at one time. You're going to use chain. Compress is cool. Compress applies a true-false filter to each item in a list, depending on whether, so you can think of it like I zip the two things together, and then if it's true, I keep it. If it's false, I throw it away. So compress accepts a list of selectors and an iterable, and it will go through each time, and it will say, okay, Raymond's not a guy, Guy's not a guy, or Raymond's a guy, Guy's a guy, Sarah's a woman, Ann's a woman, and Bill is a guy. And I'm only interested in the women, so remove all the things that don't match my selector mapping. Cycle is a function within itertools here, where you can cycle through a list multiple times. So this is going to grab the same thing out of, it's going to grab the next item in people every time it's called until it gets to the end, and then it's going to start at the beginning again. This is really useful with zip. All these things combine together. All these functions combine together in really interesting and intricate ways. And this is an example here where I can use zip and cycle together because I have lots of preferences that got ordered in a weird way through a data transformation. And I have all the food up front ordered correctly, and then I have all the colors ordered correctly, but I have a list of people that's shorter than the actual list of all my mappings. So how do I combine that together? Cycle will let you cycle through that shorter list multiple times. Group by is probably my favorite function within itertools. I think it is the most useful for doing really complicated data transformations on disparate data. So here I have a list of strings, and I have a string, and I want to sort each item, each character in this string, and I want to group them together. So group by, one of its restrictions is it requires sorted data. So here I have sorted this data, and I've added a comment up there to remind you, tell you that your data needs to be sorted when you use group by, or else bad things happen. So I'm going to go through, I want to group by all the different things in this list. That's going to give me a set of key value pairs. And then I can iterate through each of those key value pairs here, get the length of each occurrence, and then it prints it out here. This is really great if you have lots of data and you want to find how often something occurs in that data, how often distinct elements happen in that data. Group by is excellent for that. Here is them mapped together, right? So the key in this case is A, and then here are all the actual items of A that were together, right? And here's the first occurrence of C, here's all the other occurrences of C. Here's the first occurrence of B, here's all the other occurrences of B. You look at this and you're like, yeah, I don't know, right? So you see this. This is my favorite example. We have a list of IDs that have different information in them. And I want to map, and I want to group them by their ID. So I have multiple objects. I have an entry in a database somewhere that maps ID 1 to, maybe I'm pulling from multiple databases. I have a database over here where this guy's ID is Raymond, and he's ID 1. And over here I have ID 1, and that's Bob, and ID 2, and that's Sue. And I need to combine them together, and I go, wait, these IDs are the same. Their social security numbers are the same. Their phone numbers are the same. Something's wrong, right? I want to be able to group them together so that I can maybe do more intelligent analysis on that. this lets me do that. I can pull from multiple sources, have them all just kind of grouped together in the same list, and then group them together with group by. So here 1 shows us each item that maps to 1, and 2 shows us Sue, which isn't the problem in this case. Here's another example. I have, from this database, I have ID maps to my name, and I have, over here, my ID maps to my email. So this is my email database. This is my name database. So I pull from 2 different sources, combine them together in one thing, and then I can group by them. And then I can go through, combine all our other stuff together. So I can do either a map or list comprehension here, where I am getting for each one of these, 1 with the value in this list, select by our ID. That's what I want you to group on for this object. Group on those objects, combine them together, and then I'm going to I always stop on this slide. Always stop on this slide. It's a bit mind-bending.
So you have a list of dictionaries?
Yeah. Anyways, I'm grouping them together. This will be online. You can go through it and try to figure out what I'm doing. I have a whole thing about this at the end of kind of where we are. But anyways, it gets me this. Like, this is the result here, this group by here. So I've done this fancy stuff, fancy stuff, and I've ended up with my ID where I've mapped my name to my email from 2 different sources in one place. There's a reason that even though this is not readable, and as we say as Python guys, readability counts, there's a reason you might want to use this. There's a reason you might want to do this. And the reason is, it's mathematically sound, right? There's no real if statements in there. There's no, you could write a proof about this and say it's always going to work this way, always for this data. It's always going to accomplish the same thing. It's not going to be, it's less prone to error and breakdown. This is why pure functional languages like Haskell are used pretty heavily in finance, particularly in the stock market, is because they can write these high performance, high-end functional data transformations in real time and know that they're always going to transform the data the same way. Like a mathematician, quant, is sitting there writing out a mathematical proof, and then they write the code for it. Because at that point, you're trading at high-speed trading, right? Milliseconds can cost you millions of dollars. So it's important to do that. If you're doing large-scale data transformations, writing this out, even though it's not immediately readable, even though I'm the guy who wrote this, and I'm coming back to it and I'm going, I don't remember exactly what I was trying to do here. I know this is always going to work. So that's part of the reason that you want to use it. But you don't want to use it because if you're trying to write readable, maintainable code. So product is basically does a I don't know if I should say it's not a dot product, a cross product, right? So it's going to take this thing and map it to this thing, and this thing and this thing. It's going to pair these things together, and then it's going to do it again for these two, and it's going to do it again for these, right? So it's going to give you multiple combinations of different things. Pretty straightforward. And now I'm going to go back to my other slides and quickly go through these. Where are we at on time? Okay. So I have to apologize to you. I actually double booked conferences this year. So I got back from Gen Con last night where I've been demoing a board game that I've designed pretty much nonstop, so my voice is hoarse. It also means I didn't get to do everything I wanted to do in this talk. What I really wanted this talk to be on was less about the IterTools library and all the cool things in it, and actually show you guys real examples of like, here's some really weird data I got, and this is the 5 lines of code that translates all that data into this thing that I actually need. That's what I wanted to show you. Next year, I'm going to give a different talk. I'm not going to call it Super Intermediate Python, but it will be on functional programming, and I will have that. If you come out, I promise you, I will show you how to take really weird data-looking stuff, apply functional programming principles to it, and get clean-looking stuff out of it. So my apologies to you guys. So why use functional programming in Python? Object-oriented programming is not always mathematically sound. If I write classes and those classes do other classes, those classes have functions in them, and I'm using this object-oriented method, I have, if you've got Java in your Python, God forbid, you've got factories and builders and all these other things going on in enterprise code, like, that stuff is prone to error, right? There's no proof, there's no easy mathematical stuff that you can write out and say this is always going to work this way, as far as hard proof goes. But functional programming is mathematically provable. Everything in the IteraTools library and in like PyTools and some other functional libraries, you can write proofs about them. You say this code I can prove 100% of the time will do exactly what I say it's going to do, and write out that mathematical proof. So downsides to this, why you shouldn't use it, it's not very readable. I recommend if you're writing Python code, you should be focusing on readability first, always. Don't write code like everything you see here unless you know you have large data transformations you need to do and you want it always to be repeatable. That's the only reason you should use functional programming, in my opinion. My opinion is often wrong, but that's how I think about things. I think it's okay to write occasionally some functional programming code in Python that are small blocks. I'm trying to translate this into something else. I recommend you comment the hell out of it. Because to somebody who's not familiar with the IteraTools library or somebody else, especially in project code, it's going to be hard to read. It's going to be hard to go to reason about. Functional programming code can be difficult to extend and maintain. Same reason. There's a lot of times when I've had big data transformation code. I mean, it's pretty terse and it's very compact, but I've thrown away everything I wrote and I rewrote it from scratch, that particular function that did that data transformation. Because like you saw there earlier, I'm looking at it, I'm like, this is going to take me a minute to grok. I'm going to have to really sit here and think about this a little bit. Which goes back to another reason why you should use it. It forces you to think about what this is doing. Right? You have to sit, when you're programming in a functional style, you have to sit there and really think about what you're doing, how the data is being translated. Which for me, I often overlook and overglance things when I'm doing things in a more like object-oriented style. So it's good for me to occasionally sit down and really think things through. Your code organization can suffer. I have not found a good way to organize a lot of functional stuff. But on the flip side of that, I've actually used functional programming concepts like filter, map, and reduce to dry up code. When you start getting into it, and hopefully in the next talk I give on this, you can do some really gnarly looking stuff with dictionaries and functions that map to other functions within dictionaries using like a functional style. So use this responsibility. It's great for data transformations, great for data mining, great for mathematically provable starts, and it'll give you superpowers. Any questions?
How does zip operate if it's not one-on-one? So if your first list has 6,
It truncates.
second one has 7.
It truncates.
Can you repeat the question?
Oh yeah, the question was, how does zip handle if you have two lists that are not of equal size? So I have a list that is 4 long and I have a list that is 6 long. What happens to the data? And the answer is that it truncates the longer list. So only map the first 4 things that it sees. It uses the smaller number. Yes?
Part of the unreadability is like you squeeze everything into like one line. You could have easily the left-hand side of what you were operating into something that would have been a function that you could have called, and have that result be something that does code. That's clearly, I mean, with a real dot string.
Absolutely.
I mean, functional doesn't have to be unreadable.
So the comment was that functional doesn't have to be unreadable because I was compacting one-liners together, particularly on that one function where I had like three things kind of combined together. I could have broken up that a little bit, I think was the comment, and that don't let that discourage you. You can write functional code in a way that is more readable than what I've presented. Quick question for you guys. How do you feel about my presenting style? I've tried to be a less animated this time than I was a couple years ago, where I was jumping around all over the place. I'm trying to be a little bit more conservative so that it's less distracting. What are your thoughts? You like that? Don't like that? Am I boring?
Slow down a little bit. Need a little bit more time to absorb some of that.
Okay.
Like, okay, how does this work? Yeah. Need a little more time to absorb.
Cool stuff. All right. Thank you guys so much for coming. How did I do on time? How much time do we have left?
We still have like 20 minutes.
Really? We have 20 minutes left. I have another talk. You guys want to hear another talk? Yeah. What's up?
So there's also IZIP longest in intervals, where you can say pick a longer one and then fill it in with none or something else.
Yes. So that on the zip question earlier was what happens if you use zip? It truncates the small list. There is an IZIP longest in Python 2. In Python 3, it's called zip longest. Or Python 3, yeah, zip longest, which will take the longer and then just pad the rest of the data. So you can use the longer amount rather than the shorter amount.
I think also the answer to your question, the question earlier about the map is a generator versus the other one, which is generator. List comprehension.
Okay. So the answer, there was a question asked earlier in the day that was, what is the difference between using map and a list comprehension? And that was the answer that we've heard from the crowd is that list comprehensions represent as iterators, and map will handle it as a generator.
Map can also be more performant if you're calling the same function inside of list comprehension.
Map can also be more performant if you're calling the same function within a list comprehension.
But I think I was just reading that the style guide recommends using list comprehension over map for readability.
Very cool.
In Python 2, there used to be a scoping problem with list comprehensions where if you used variable name, it could overwrite inside the same scope. Like if you had a function with parameter x, you use x inside list comprehension, it would overwrite your x. That's been fixed in 3. So it's fixed in 7 as well.
Stuff. I missed part of it. I'm sorry.